proximity fuse is a fuse that detonates an explosive device automatically when the distance to the target becomes smaller than a predetermined value. Proximity fuses are designed for targets such as planes, missiles, ships at sea and ground forces. They provide a more sophisticated trigger mechanism than the common contact fuse or timed fuse. British military researchers Sir Samuel Curran and WWII Butement invented a proximity fuse in the early stages of World War II under the name VT, an acronym of variable time fuse. The system was a small, short-range, Doppler radar that used a clever circuit. However, Britain lacked the capacity to develop the fuse, so the design was shown to the United States during the Tizard Mission in late 1940. The fuse needed to be miniaturized, survive the high acceleration of cannon launch, and be reliable. Development was completed under the direction of physicist Merle A. Tuve at the Johns Hopkins University Applied Physics Lab. Over 2,000 American companies were mobilized to build some 20 million shell fuses. The proximity fuse was one of the most important technological innovations of the war. It was so important that it was a secret guarded to a similar level as the atom bomb project or D-Day invasion. Admiral Lewis L. Strauss wrote that, one of the most original and effective military developments in World War II was the proximity, or VT, fuse. It was of incalculable value to both the Army and Navy, and it helped save London from obliteration. While no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended. The fuse was later found to be equally useful, causing artillery shells to explode in air bursts, greatly increasing their anti-personnel effects. The Germans were supposedly also working on proximity fuses in the 1930s, based on capacitive effects rather than radar. Research and prototype work at Rheinmetall were halted in 1940 to devote available resources to projects deemed more necessary. In the post-WWII era, a number of new proximity fuse systems were developed, including radio, optical and other means. A common form used in modern air-to-air weapons uses a laser as an optical source and time of flight for ranging. History: before the proximity fuse's invention, detonation was induced by direct contact, a timer set at launch, or an altimeter. All of these earlier methods have disadvantages. The probability of a direct hit on a small moving target is low. A shell that just misses the target will not explode. A time or height-triggered fuse requires an accurate prediction. If the setting is wrong, then even accurately aimed shells may explode harmlessly before reaching the target. With a proximity fuse, the shell or missile need only pass close by the target at some time during its trajectory. The proximity fuse makes the problem simpler than the previous methods. Proximity fuses are also useful for producing airbursts against ground targets. A contact fuse would explode when it hit the ground. It would not be very effective at scattering shrapnel. A timer fuse can be set to explode a few meters above the ground, but the timing is critical and usually requires observers to provide information for adjusting the timing. Observers may not be practical in many situations, the ground may be uneven, and the practice is slow in any event. Proximity fuses fitted to such weapons as artillery and mortar shells solve this problem by having a range of preset burst heights above ground that are selected by gun crews prior to firing. The shell bursts at the appropriate height above ground. World War II. Design equals. In the late 1930s the UK was working on a variety of developments to increase air defence efficiency. Into this step WWII Butement, designer of radar sets CDCHL and GL, with a proposal on October 30, 1939 for two kinds of radio fuse. A radar set would track the projectile, and the operator would transmit a signal to a radio receiver in the fuse when the range, the difficult quantity for the gunners to determine, was the same as that of the target, and a fuse would emit high-frequency radio waves that would interact with the target and produce, as a consequence of the high relative speed of target and projectile, a Doppler frequency signal sensed in the oscillator. The first radar proximity fuse was proposed by Butement, Edward S. Shire, and Ernest F. H. Thompson, in a memo to the British Air Defence Establishment in May 1940. A breadboard circuit was constructed by the inventors and the concept was tested in the laboratory by moving a sheet of tin at various distances. Early field testing connected the circuit to a thyratron trigger operating a tower-mounted camera which photographed passing aircraft to determine distance of fuse function. Prototype fuses were then constructed in June 1940, and installed in unrotated projectiles fired at targets supported by balloons. Between September 1939 and 1942, at the request of Sir John Cockcroft of the Ministry of Supply, the radar team at PI Limited carried out pioneering experimental work on radio proximity fuses for anti-aircraft artillery shells. This work included the design, in-house manufacture and testing of suitable miniature thermionic valves. PI's research was transferred to the United States as part of the technology package delivered by the Tizard Mission when the United States entered the war. The British ordered 20,000 special miniature tubes from Western Electric Company and Radio Corporation of America, and an American team under Admiral Harold G. Bowen, Sr. correctly deduced that the tubes were meant for experiments with proximity fuses. The details of these experiments were passed to the United States Naval Research Laboratory and National Defense Research Committee by the Tizard Mission in September 1940, in accordance with an informal agreement between Winston Churchill and Franklin D. Roosevelt to exchange scientific information of potential military value. Following receipt of details from the British, the experiments were successfully duplicated by Richard B. Roberts, Henry H. Porter, and Robert B. Broad under the direction of NDRC Section T Chairman Merle Tuve. Lloyd Berkner of Tuve staff devised an improved fuse using separate tubes for transmission and reception. In December 1940, Tuve invited Harry Diamond and Wilbur S. Hinman, Jr., of the United States National Bureau of Standards to investigate Berkner's improved fuse. The NBS team built 6 fuses which were placed in air-dropped bombs and successfully tested over water on May 6, 1941. While working for a defense contractor in the mid-1940s, Soviets by Julius Rosenberg stole a working model of an American proximity fuse and delivered it to the KGB. In the USA, NDRC focused on radio fuses for use with anti-aircraft artillery, where acceleration was up to 20,000 g as opposed to about 100 g for rockets and much less for dropped bombs. In addition to extreme acceleration, artillery shells were spun by the rifling of the gun barrels to close to 30,000 rpms, creating immense centrifugal force. Working with Western Electric Company and Raytheon Company, miniature hearing aid tubes were modified to withstand this extreme stress. The T3 fuse had a 52% success against a water target when tested in January, 1942. The United States Navy accepted that failure rate, and batteries aboard cruiser USS Cleveland tested proximity-fused ammunition against drone aircraft targets over Chesapeake Bay in August 1942. The tests were so successful that all target drones were destroyed before testing was complete. A particularly successful application was the 90mm shell with VT fuse with the SCR-584 automatic tracking radar and the M9 electronic fire control computer. The combination of these 3 inventions was successful in shooting down many V-1 flying bombs aimed at London and Antwerp. In Germany, more than 30 approaches to proximity fuse development were underway, but none saw service. These included acoustic fuses triggered by engine sound, one based on electrostatic fields developed by Rheinmetall Borsig AG, and radio fuses. A German neon lamp tube and a design of a prototype proximity fuse based on capacitive effects was received by British intelligence in mid-November 1939. By the end of the war, only one was actually in production, a complicated radio proximity fuse for rockets and bombs. VT the Allied fuse used constructive and destructive interference to detect its target. The design had 4 tubes. One tube was an oscillator connected to an antenna. It functioned as both a transmitter and an autodyne detector. When the target was far away, it would reflect little of the oscillator's energy back to the fuse and have almost no effect on the circuit. When a target was nearby, it would reflect a significant portion of the oscillator's signal back to the fuse. The amplitude of the reflected signal indicated the closeness of the target. This reflected signal would affect the oscillator depending on the round-trip distance from the fuse to the target. If the reflected signal were in phase, the oscillator amplitude would increase and the oscillator's plate current would also increase. If the reflected signal were out of phase, then the plate current would decrease. The distance between the fuse and the target is not constant but rather constantly changing due to the high speed of the fuse and any motion of the target. When the distance between the fuse and the target changes rapidly, then the phase relationship also changes rapidly. The signals are in phase one instant and out of phase a few hundred microseconds later. The result is a heterodyne beat frequency that indicates the velocity difference. Viewed another way, the received signal frequency is Doppler shifted from the oscillator frequency by the relative motion of the fuse and target. Consequently, a low-frequency signal corresponding to the frequency difference develops at the oscillator's plate terminal. Two additional amplifiers detected and filtered this low-frequency signal. If the amplified beat frequency signal is large enough, then it triggers the fourth tube. The thyrotron conducts a large current that sets off the electrical detonator. There were many shock hardening techniques including planar electrodes and packing the components in wax and oil to equalize the stresses. Production First large-scale production of tubes for the new fuses was at a General Electric plant in Cleveland, Ohio, formerly used for manufacture of Christmas tree lamps. Fuse assembly was completed at General Electric plants in Schenectady, New York and Bridgeport, Connecticut. By 1944 a large proportion of the American electronics industry concentrated on making the fuses. Procurement contracts increased from $60 million in 1942, to $200 million in 1943, to $300 million in 1944 and were topped by $450 million in 1945. As volume increased, efficiency came into play and the cost per fuse fell from $732 in 1942 to $18 in 1945. This permitted the purchase of over 22 million fuses for approximately $1 billion. The main suppliers were Crossley, RCA, Eastman Kodak, Mackay Norris in Sylvania. There were also over 2,000 suppliers and sub-suppliers, ranging from powder manufacturers to machine shops. It was among the first mass production applications of printed circuits. Deployment Vannevar Bush, head of the U.S. Office of Scientific Research and Development during the war, credited the proximity fuse with three significant effects. It was important in defense from Japanese kamikaze attacks in the Pacific. Bush estimated a seven-fold increase in the effectiveness of 5-inch anti-aircraft artillery with this innovation. It was an important part of the radar-controlled anti-aircraft batteries that finally neutralized the German V-1 bomb attacks on England. It was used in Europe starting in the Battle of the Bulge where it was very effective against German divisions, and changed the tactics of land warfare. At first the fuses were only used in situations where they could not be captured by the Germans. They were used in land-based artillery in the South Pacific in 1944. They were incorporated into bombs dropped by the USAAF on Japan in 1945, and they were used to defend Britain against the V-1 attacks of 1944, achieving a kill ratio of about 79%. There was no risk of a dud falling into enemy hands. The Pentagon had decided it was too dangerous to have a fuse fall into German hands because they might reverse engineer it and create a weapon that would destroy the Allied bombers, or at least find a way to jam the radio signals. The Pentagon refused to allow the Allied field artillery use of the fuses in 1944, although the United States Navy fired proximity-fused anti-aircraft shells during the July 1943 invasion of Sicily. After General Dwight D. Eisenhower demanded he be allowed to use the fuses, the VT fuses were used in the Battle of the Bulge in December 1944, when they made the Allied artillery far more devastating, as all the shells now exploded just before hitting the ground. It decimated German divisions caught in the open. The Germans felt safe from timed fire because they thought that the bad weather would prevent accurate observation. The effectiveness of the new VT-fused shells exploding in mid-air, on exposed personnel, caused a minor mutiny when German soldiers started refusing orders to move out of their bunkers during an artillery attack. U.S. General George S. Patton said that the introduction of the proximity fuse required a full revision of the tactics of land warfare. The Germans started their own independent research in the 1930s, but the program was cut in 1940, likely due to the FAR 1/4 Rare Directive that, with few exceptions, stipulated all work that could not be put into production within 6 months was to be terminated to increase resources for those projects that could. It was at this time that the Germans also abandoned their magnetron and microwave radar development teams and programs. Many other advanced and experimental programs also suffered. Upon resumption of research and testing by Rheinmetall in 1944, the Germans managed to develop and test fire several hundred working prototypes before the war ended. Sensor types Radio frequency sensing is the main sensing principle for artillery shells. The device described in World War II patent works as follows. The shell contains a microtransmitter which uses the shell body as an antenna and emits a continuous wave of roughly 180–220 MHz. As the shell approaches a reflecting object, an interference pattern is created. This pattern changes with shrinking distance. Every half wavelength and distance, the transmitter is in or out of resonance. This causes a small cycling of the radiated power and consequently the oscillator supply current of about 200–800 Hz, the Doppler frequency. This signal is sent through a bandpass filter, amplified, and triggers the detonation when it exceeds a given amplitude. Optical sensing was developed in 1935, and patented in Great Britain in 1936, by a Swedish inventor, probably Edward W. Brandt, using a petoscope. It was first tested as a part of a detonation device for bombs that were to be dropped over bomber aircraft, part of the UK's Air Ministry's Bombs on Bombers concept. It was considered for use with anti-aircraft missiles fired from the ground. It used an toroidal lens that concentrated all light from a plane perpendicular to the missile's main axis onto a photocell. When the cell current changed a certain amount in a certain time interval, the detonation was triggered. Some modern air-to-air missiles use lasers to trigger detonation. They project narrow beams of laser light perpendicular to the flight of the missile. As the missile cruises towards its target, the laser energy simply beams out into space. As the missile passes its target, some of the energy strikes the target and is reflected back to the missile, where detectors sense it and detonate the warhead. Acoustic sensing used a microphone in a missile. The characteristic frequency of an aircraft engine is filtered and triggers the detonation. This principle was applied in British experiments with bombs, anti-aircraft missiles, and airburst shells. Later it was applied in German anti-aircraft missiles, which were mostly still in development when the war ended. The British used a Rochelle salt microphone and a piezoelectric device to trigger a relay to detonate the projectile or bomb's explosive. Naval mines can also use acoustic sensing, with modern versions able to be programmed to listen for the signature of a specific ship. Magnetic. Magnetic sensing can only be applied to detect huge masses of iron such as ships. It is used in mines and torpedoes. Fuses of this type can be defeated by degaussing, using non-metal hulls for ships, or by magnetic induction loops fitted to aircraft or towed buoys. Pressure. Some naval mines are able to detect the pressure wave of a ship passing overhead. VT and variable time. The designation VT is often said to refer to variable time. Fused munitions before this invention were set to explode at a given time after firing, and an incorrect estimation of the flight time would result in the munition exploding too soon or too late. The VT fuse could be relied upon to explode at the right to near, which might vary from that estimated. One theory is that VT was coined simply because Section V of the Bureau of Ordnance was in charge of the program and they allocated it the code letter T. This would mean that the initials also standing for variable time was a happy coincidence that was supported as an intelligent smokescreen by the Allies in World War II to hide its true mechanism. An alternative is that it was deliberately coined from the existing VD terminology by one of the designers. Developed by the U.S. Navy, development and early production was outsourced to the Wurlitzer Company. at their barrel organ factory in North Tonawanda, New York. Gallery. See also, Allied technological cooperation during World War II, contact fuse, M734 proximity fuse. Notes. References. Bibliography, Baldwin, Ralph B., The Deadly Fuse, The Secret Weapon of World War II, San Rafael, California, Presidio Press, ISBN 0-89141-087-2. Baldwin was a member of the team headed by Tuve that did most of the design work. Baxter, James Finney III, 1946, Scientists Against Time, Cambridge, Massachusetts, MIT Press, ISBN 978-0-262-52012-6, Bureau of Ordnance, VT Fuses for Projectiles and Spin-Stabilized Rockets, Ordnance Pamphlet, OP 1480. U.S. Navy Bureau of Ordnance, Bush, Vannevar, Pieces of the Action, New York, William Morrow and Company, Incorporated. Hogg, Ian 5, British and American Artillery of World War II, Green Hill Books, ISBN 978-1-85367-478-5, Sharp, Edward A., The Radio Proximity Fuse, A Survey, Vintage Electrics 2. Further reading, Bennett, Geoffrey, The Development of the Proximity Fuse, Journal of the Royal United Service Institution 121, 57 ISSN 0953-3559, Collier, Cameron D., Tiny Miracle, The Proximity Fuse, Naval History 13, 43 ISSN 1042-1924 Text, EBSCO, Fuses, Proximity, Electrical, Part 1, Engineering Design Handbook, Ammunition Series, United States Army Materiel Command, July 1963, AMCP 706-211, Fuses, Proximity, Electrical, Part 2, Engineering Design Handbook, Ammunition Series. United States Army Materiel Command, AMCP 706-212, Fuses, Proximity, Electrical, Part 3, Engineering Design Handbook, Ammunition Series, United States Army Materiel Command, AMCP 706-213, Fuses, Proximity, Electrical, Part 4, Engineering Design Handbook, Ammunition Series, United States Army Materiel Command, AMCP 706-214, Fuses, Proximity, Electrical, Part 5, Engineering Design Handbook, Ammunition Series, United States Army Materiel Command, August 1963, AMCP 706-215. External links, Naval Historical Center, Radio Proximity Fuses, The Radio Proximity Fuse, A Survey Southwest Museum of Engineering, Communications and Computation, Proximity Fuse History Southwest Museum of Engineering, Communications and Computation, The Proximity Fuse, The Pacific War, the U.S. Navy, the Johns Hopkins University Applied Physics Laboratory.